Okay, so one of the things about, like this sheet I gave you, exhibit number 1, this, if you understand it, and again, I'm going to pick it up after class. I haven't decided how I want to do it Friday for the test and such. You might be able to check them out over the weekend so you can look at them, but don't write on them, okay? Because you can't have extra notes, but you can have this. Are any questions about how that whole thing's going to work? So notice that I went ahead and we've got this thing going on. What does 8M mean? What does the M mean?
Mass of the sun.
Mass of our sun, yep. So we have these 2 options. So please put phones away. That would be awesome. And we decided none of you, well, you have a child, so you can have your phone out. And your child doesn't live in this area. So put your phones away. So here's the deal. Yeah, so we have this thing going on with regard to sizes. We have something that's pretty light. And on the test, I mean, I don't want to tell you how to do your test, but if I ask you, what is our sun going to do? Guess what? Is our sun less than 8 solar masses? Yeah, just like Sol that we interviewed. This is the path, this is the path that our sun is going to go. Okay? So what the heck? I'm kind of excited about this whole thing. You'll get these back after the test. So high mass stars, check this out. We're going to talk about lives of high mass stars, or deaths of high mass stars. What are these 2 options over here?
The black hole and the
Yeah, black hole and neutron star. So I'm going to lead up to that, okay? So which one, can you see? Again, I'm going to kind of go, this would be called infographics. I don't know if you're familiar with this. It's a way of teaching. You know, there's a picture's worth a lot of words. Check out over here. Which one's got the more mass? Which one actually has a criteria? What do you think, neutron star or black hole?
black hole.
Black hole, yeah. So not only does it have to be greater than 8 times the mass of our sun, but for a black hole, it has to be greater than 25 times the mass of our sun. So right away, you kind of have some answers to some questions you might run into on Monday's test. Okay? So a lot of pictures here. This is actually a family portrait. You kind of see some star clusters here, cluster of stars, and these are kind of some different ages. If you read the caption, we've got kind of a nice active group here. We've got a forming group in this nebula, stars. We've been talking about how stars are born in molecular clouds. Hi. Come on in. We're talking about stars.
All right.
So you guys want to have a seat? So we'll finish that few slides, and then, yeah. I can decide what I want to do when y'all come. We're just glad you're here. With regard to the mass of our sun, we're talking, test question, is it 2, is it 5, is it 31? How many solar masses?
3 by 8.
8. 8 times the mass of our sun.
I'm sorry.
And so remember, you're going to have this. And so this kind of shows you the cutting, the cutoff. So high mass star.
Are we going to need to know the 8? Oh, it's in there.
It's on here.
So we
on
just need
there.
to highlight 8.
Yeah, you can. Yeah, 8 solar mass is kind of the tipping point for a high mass star. So high mass stars actually do the same thing that our star starts out doing. I don't know if you kind of remember this when we talked about what's happening in the core of our sun. These red things are actually protons. So these protons combined form what's He? What element is that?
Helium.
Helium, yeah. So these protons are actually hydrogen. So hydrogen goes to form helium, releases a lot of energy. That's what our sun is doing. But with more massive stars, we have more interesting things going on. So the CNO, what element is C?
Carbon.
Carbon. What element is N?
Nitrogen.
What element is O?
Oxygen.
Yeah. So the CNO cycle is what's happening in a star to use carbon, nitrogen, and oxygen to go ahead and kick it up a notch. Now I'll go ahead and I'll bring this out. This is the middle of my sun. Like this slide says, and kind of critical to understanding what's going on with stars is that every time it kind of right now, our sun is creating helium in its core. It's got hydrogen plus hydrogen goes to create helium. Well, eventually it's going to run out of hydrogen. I was talking to my mom about this. Okay, so it's going to blow it out and such. But that helium at some point is going to begin fusing. Helium fusion. Helium fusion. What does fusion mean? We talked about this before. It means taking atoms and squishing them together. Yeah, uniting them. And making something larger. What is that thing larger? Carbon. Okay? How long in a massive star will that happen? Will that continue to click? About 1,000 years. Okay? After helium fusion, then in the core, we have carbon fusion. What does carbon fusion create? Neon. How long does it last? 600 years. How would you compare this, like 10,000 to 1,000 to 600 years? What's happening with how long that stays long? It's getting shorter and shorter. Okay? Runs out of carbon in its core. When each time it runs out of this thing that it's fusing, it shrinks and compacts. And as it compacts, it gets hotter and more pressure to go ahead and begin fusing the next thing. So neon fusing produces oxygen. How long does that take? Just a year. Check this out. It runs out of neon, but it has a bunch of oxygen. It comes together, as in gets more and more dense. Its temperature bumps up. This is the core temperature. That's crazy. Now, our sun will never do this, but a massive star will. Okay? It makes silicon 6 months. Well, then it's got a core of silicon. It runs out of oxygen. So it takes its silicon and creates iron. How long does that last? A day. Now, this is if you're an astronomer, you're like, I'm on it. I'm going to take my telescope, and I'm so looking at that star. But we really can't tell when that day is. But you talk about 24 hours or so for it to go ahead and basically take its silicon in its core and make iron. What's the symbol for iron?
Fe.
Fe, yep, the symbol for iron is Fe. Now this is actually the beginning, this is actually the end. Because you're like, well, it'll go ahead and get a hotter temperature and it will fuse iron to form something heavier. That's not happening, okay? So kind of right before it dies, this is kind of what we have. We have the hottest region in the core making the most complicated sort of fusion reactions. And then outside we have these what we call shell fusion areas. Okay, so it's kind of like an onion. So yep, iron ash from silicon fusing to form iron. So yeah, if we knew when the star was going to blow, we totally would be looking at it. But we have seen stars blow. I'm going to show you some pictures here and some photographs. Our best bet of finding a star that blew up is to look at other galaxies. Now remember how galaxies work. They're outside our galaxy. So we look at other galaxies for a blow up. We call it a supernova. And that just blows my mind. It's so bright that we can see it from our galaxy. It's amazing. All right. So why is iron the tipping point? This tries to kind of show you. There's this thing in science called exothermic energy is released versus, that's what we're counting on for a star to do, versus endothermic energy is required. And energy is released during all of those fusions, okay, up to iron. And after iron, if you want to fuse iron to get something heavier, it's what we call endothermic. It requires energy. So you're like, dude, that's not happening. Actually, there's two types, and I'm going to put this on your test because we talked about what's happening in our sun. This is fusion, okay? If I take something big like a uranium atom, we do it all the time. If we split an atom, that's called fission, F-I-S-S-I-O-N, like you see up here after iron. So fission means breaking apart, fusion means breaking together. So here's the deal. We could take something after iron, something bigger than iron, and break it apart and get energy, but we can't fuse things together. That's why it's a tipping point, kind of an abrupt end. All right, so this is kind of interesting, I think. You kind of see these jags up and down and up and down. This is talking about how much of that element is there in the universe, not in our solar system or not in our planet. How much of that element is there in the universe? And as it turns out, the even ones are much more abundant than the odd ones. And it all has to do with whenever you add a helium you're adding 2. Helium, atomic number 2, 2 protons. So by twosies is much more abundant. All right, so what happens when it blows up? We call that a supernova. And tomorrow, right before your test, I'm going to talk about binary stars. I have one more handout to give you. And we're going to see that there's 2 types of supernovas. Don't blame me. They should have called it something else.
Are you doing the video?
I'm going to do video.
Okay.
Yep, I'm going to do one kind of short part of lecture and a video. So what happens is basically, like we talked about, what's the last thing that happens? Silicon fuses to form iron, but iron won't fuse, right? So, well, what happens there? Well, it can't get any smaller to create energy, okay? So basically, let's make sure I get it. Okay, so I'll point to there. What did you guys tell me? All in color, and again, you'll have this for your test on Monday. What did you tell me? There are 2 options for kind of that little nubbin after it blows up?
Total neutron star.
Yep. So what a neutron star is basically, it's so cool. You have the blow up thing, and I'll try to describe that, but kind of in addition to the blow up thing, you have a little orb of something left. And that little orb actually has taken the matter, like the atoms that made up that star, and it has squished the atoms together so that the electrons, we know what electrons are, right? The electrons and the protons have squished together to make neutrons. It's like a neutron soup. It's like what are the atoms with this neutron star? Neutrons. Okay? They're not really normal atoms, it's just neutron soup. I think that is so cool. But with a neutron star, that's neutron star, the neutrons, they at least kind of keep it from collapsing any further. Because when we talk about a black hole, basically those neutrons can't keep it from collapsing anymore. The neutrons collapse in on themselves and they create a hole, a rift in the fabric of space and time that object is in. Okay? If neutron degeneracy can't keep it up from squishing, then it's like, dude, it collapses in on itself. It's like a cartoon. Okay? Black holes. I'm thinking we're going to go ahead and I'm going to, in Unit 4, after your test after Thanksgiving, I think I'll pull that up. I'll talk a little bit about black holes. Well, what's the blow up part? So those are the 2 options. You guys told me that after it blows up, we're going to either have neutron soup, neutron star, or we're going to have a black hole. Neutron star means the neutrons stop collapsing. Black hole means there was so much crap, which is 25 solar masses, basically created a hole. And some people think that that hole in what we call space-time, fabric of space-time, that hole actually could be a hole that goes to another universe. I'm not so sure. It might be.
Fly a spaceship in there, see what happens.
Yeah, fly spaceship like Stargate, like Stargate universe. They fly.
Or a satellite. Just shoot
Yeah.
a satellite.
Actually, there has been, some scientists have built a gizmo to get a close look up of a black hole. I can't remember the details. Interesting. So what's up with the blow up part? Well, I think the bottom here talks about stiffening. Basically that iron stiffened and you get basically stuff coming in because it's shrinking, it's not creating fusion anymore. And it loses that outward pressure, so you have stuff coming in, and it hits the core, and then it's going out. So basically you have that stuff going out that hit the core, and you have stuff still coming in. So you have going out and coming in. It's chaos. And that's actually part of it, just blowing up. Okay? This actually is, this is my chart of Messier objects. These are M objects. Clear up here, M1, the first one that he cataloged, actually is the guts of a star that blew up. SN stands for supernova, and this is actually Messier object 1. So we call this a supernova remnant. When did it blow up? About 1054 AD, not BC, AD. Okay. So yeah, 1054. And I'm thinking I got this right. Japanese, maybe, astronomers actually captured this event and in saying it happened. So just a bright region of the sky for about a couple of weeks. We'll kind of talk about the brightness decay. Here's one in our lifetime. Well, my lifetime anyway. 1987. Okay. So this is the before it blows up. This is right after it blows up. Okay. I'm thinking this was in our own, I have to double check, in our own galaxy. These are in other galaxies, so you can kind of see the blow up. This is before the blow up. Blow up. Blow up. Blow up. Blow up. So you're like, well, how do we know when they're going to go? So actually, we have observers around the world that have telescopes that take these pictures. They're basically, all they do all night long is look at these galaxies, take pictures, and try to see if something ever happens. So those are just galaxies. This is a supernova remnant that is actually shown in the different wavelengths. That's the same supernova remnant. Star blowing up, supernova remnant. You kind of see the ejection of material from it. This one you're going to see, this is on a nebula region, but you're going to see it kind of blown up. This is really pretty. So that actually, that ring is what you saw on the previous slide. You kind of see how the ring of material, it's delayed, but it looks like it got lighter in those 6 years. It became brighter. So over time, this is a brightness curve. Over time, they actually get dimmer. So you guys told me that the negative numbers, actually negative magnitudes would be up here. So we have about, remember 6 magnitude of plus 6 is about our naked eye. So 5 would be better than our naked eye. So here there's the brightness blip. And then over the course of a couple weeks, it dims significantly. But you can see this is over 1,000 days, how the brightness changes, goes down. Crab Nebula. All right, so this actually, the Crab Nebula is associated with supernova remnants. And you can see this region right here, it's actually a neutron star. In the next few slides, I'm going to talk about that neutron star right there. So here's the Crab Nebula, a little different picture than we saw in the previous slide. There's a neutron star. And back in 1967, we didn't quite understand this whole, where's my sheet? Okay, we're still trying to flesh this out. We're still trying to flesh it out, actually. But in 1967, kind of thought this was the deal, understood the 2 options for a massive star. But in 1967, this is where the theoretical intersects with the observational. Actually observed a radio signal coming from this remnant, this supernova remnant. Radio signal coming from the middle of this star that blew up. And as it turns out, that radio signal, and this is what the radio signal would look like turned on, it's on, off, on, off, on, off, on, off. But how frequently is it? 0.033 seconds is this one cycle. So it's very quick. So it's like, and then they started to look for radio signals other places in the universe, and they came up with a bunch of radio signals. So we think if something can do that, it's probably intelligent, probably trying to send us some sort of, well, not trying to send us something, but there is intelligent life there. So these signals started out, they were called LGM, standing for Little Green Men, okay? And as it turns out, they were, I'll try to show you why, an indication of a neutron star. So this is why the neutron star sends out those signals. Now those signals aren't called little LGMs anymore, little green men. Those signals are called pulsars. Pulsars come from neutron stars. Why do neutron stars send pulsar signals? Well, this figure, both these figures, and I have one on the next slide, kind of try to show you why that would be. A neutron star is a crazy object. It's got a lot of spin to it, because basically, as a star was spinning, and it's like, I think we talked about the conservation of angular momentum maybe, but if a skater takes her arms out, and if she takes her arms, brings her arms inwards, what happens to how fast she spins? It's faster and faster. And so that's kind of what sort of phenomenon we have going with this neutron star that is now the little nubbin of used to be a big humongous star. So we have a lot of spin here, which actually creates a magnetic field, and out those magnetic fields, out that magnetic field that goes from pole to pole, we have this squirt of energy. So it's a squirt of energy that we're actually seeing hit us. So let's see, how do I say this? If you guys are the Earth and I am the squirt of energy that is rotating, I kind of go like, I'll make myself rotate kind of this way. Okay, so you'll go blip, 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 blip. So my little squirt of energy from a neutron star is actually passing you guys. You guys are picking up that squirt of energy as a radio signal. That's coming from a neutron star. Sometimes they're called like lighthouse. They have this lighthouse thing going. This one is showing you that you guys can be where you are. You guys are Earth, and see this neutron star is spinning. So it goes blip, 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 and actually it kind of looks like the way the little cones of energy are. You guys are going to get it both sides. Go blip, 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 blip. Okay, so anyway, pulsars are related to neutron stars that way. I have some pictures for you. Is that it? Dang. Well, let's see. I'm going to go ahead and hand out, because I brought it with me, my binary stars. Let's see if we can knock this one out. I'll make it tomorrow easier. This is the last bit. Unit 3. 4. So, I hope I remember to say it. I think I will. Actually, this topic that we're talking about is actually related to the speaker that's speaking a week from yesterday, the Tuesday of Thanksgiving. And I've got information up here if you want to go. This would count as a lab. Ah, that caught your attention. Kids are welcome. I'm going to be there, soaking it up. So feel free to come up with your little phones and take a picture of this information if you want to come. This would count as a lab. So let's see how it would relate to anything we would remotely cover in this class. So if I asked you how many stars in general have a companion star, there's 2 of them together, would you say that a lot of stars have companion stars, not many stars have companion stars, no stars have companion stars? What do you think? Not many? 2/3. About 2/3 of the stars up there actually was born with a sibling. And so they kind of orbit each other. So this is quite possible. Okay? So the way this topic goes is these are a pair of stars that were born in the same molecular cloud. These pair of stars might have been part of a nursery, stellar nursery, cluster of stars. But these stars are so intimately connected that they actually have a common center of mass. They orbit each other. And we kind of talked about that before. So which star is hotter, the blue one or the red one? Blue. Yes, blue is hotter. Which one lives its life more quickly, the blue or the red one? The blue. The blue one, more massive, hotter, actually then runs through its fuel more quickly. And so the blue one is going to live a faster life. This one actually, if I kind of go down here, A to B to C, in B what's happening is that blue one actually has become a swollen giant. It's become so swollen that actually, can you see it's depositing some of its swollen matter on its companion, okay? So now its companion, who is just minding its own business, is getting new stuff from its mate there, okay? So why does this one become blue? What do you think? Yeah, because it's getting hotter because it got extra stuff from its buddy. Okay, so we could have that's kind of what happens, or what can happen, is they have different parts of different lives. Well, let's change it up a little bit. Let's go ahead. What this caption says is we're going to consider, and let's see if I can find my pen here. Consider if we have a retired white dwarf. Okay, and it is actually on in a system with a low mass star. Okay, I'll put all these up here. Oh, okay. So here we go. I'm going to call this guy a white dwarf. WD for white dwarf. Okay, this guy actually is kind of going more slowly, but he becomes a giant. Okay, basically we have the white dwarf getting dumped on. Let's see, I don't know how, I can't think of how to ask this in the form of a question, but white dwarfs are retired. White dwarfs are like, dude, I'm done. They're like grandparents. They're like, y'all raise your kids. Okay, I'm done. So what happens with, when it gets new stuff, is it's like, okay, whatever. It says, it basically gets more stuff to the point of it comes out of retirement. Okay, it comes out of retirement. Notice that this caption says that this ring around the retired star, the white dwarf, actually begins to glow. This ring, this happens a lot in astronomy, where if this is the white dwarf, this is the ring of material coming from a companion. It's basically, if we rub our hands together, what happens? They get warm. They get warm. So if basically the material in that ring is getting warmer and warmer and warmer. Where did the material come from? It's companion. All right. So what can happen then is the material can get so hot, this kind of says it can get so hot that it can begin nuclear fusion. Isn't that strange? Okay, so it's getting stuff from its companion, from hot, and it has to get dense enough that basically it begins nuclear fusion, which is just crazy to me. But here's the deal. When it had nuclear fusion in its core, that's fine, because it was like that process had all these layers of sun on top of it in the core. When it begins nuclear fusion here, guess what? It's very much like I call it throwing off a blanket. It's like in the middle of the night when you go, whew, I'm too warm, and I'm going to kick off my blanket. Okay, and then I'm going to get cold, and I'll put it back on, and warm it up on my blanket. Okay, so that sort of kickoff is associated with the nuclear fusion, and that's actually what we call a nova event, N-O-V-A. Actually, that's on your sheet, so let's get a test now. So I mentioned that actually. It's like our blanket. We kick it off, then we get cold, we put it back on again. So here's the deal. When the retired star blows off that extra material it got from its companion, because it's like, it's nuclear fusion, it's like, I can't hold on to it. Guess what? If its star is still bloated, it gives me more material. Okay? Nuclear fusion. Nova events, N-O-V-A, nova events can reoccur, and they do. They reoccur. Nova events. But it's a bright name. Supernova events. When a star blows up, can that reoccur? No. It's like Humpty Dumpty fell off the wall, and you cannot put Humpty Dumpty back together again. But this can reoccur. Well, let's take it up a notch. And actually, this is a good place to, I think I'm going to take it up a notch. So bring those sheets with you tomorrow. And we'll pick up here when we left off just a few slides, video, take notes, and I'll take your stuff again. So again, put your stuff, like if you take your stuff and put it in the
Live star.
Thank you, live to start. Yes.
You want to all right?
I got that.
Oh, yeah.
What do you guys think? Do you guys want these to study over the weekend, or are you okay if I just give them? Do you want to take yours home to look at it and stuff? How about you guys? I think I'll ask you tomorrow. If you take it home though, you're responsible to bring it back. Friday, I meant Friday, that's fine. Take it home Friday. You're responsible to bring it back. I'll keep it. Good job, you're actually youngsters.